fellow developers. As you know, getting software correct is hard, and getting security correct is even harder. And being perfectly secure, but unable to communicate with others, is pointless. So this is the story of implementing transport layer security in Erlang, and the trade-offs that we have faced. So to start with, I'd like to make one thing clear. SSL and TLS is the same protocol. It's just different versions, and they kind of changed the name in the middle. And so what does this protocol do? Well, it wants to give us three things, actually. So it wants to give us data privacy. And that means that only the sender of the message and the receiver of the message should know the content of the message. And we do this with symmetric encryption of the payload data. And also we want to have integrity. So we want to make sure that when we send the message, nobody can manipulate the message before it turns up at the receiver. Yes, so we do this with message authentication codes. And authenticity is about making sure that the person that sent the message is actually who they claim to be. And these are very important properties. And they are hard to achieve, but there are many algorithms that you can use to try to achieve this. But you have to agree on a common ground so that you can communicate. And this is what the TLS handshake is about, what the TLS protocol does for you. So our journey, it starts in 2009. And we had this SSL application in Erlang. And it was really ill-scaled and very slow. And nobody wanted to use it. Nobody wanted to contribute to it. They all made their own solutions. So what should we do about it? Should we do a better adaptation to OpenSSL? Is the C programming language really a good choice to do the TLS protocol? And when it comes to security, you should really use the best tool for to solve the problem. And that goes for software in general too, of course. And also, if we would do it in Erlang, we could get access to the socket in a different way than if we would use OpenSSL. So we could easily do things like active N and active ones, and maybe we want to upgrade the TCP connections to TLS connections. So this becomes much easier if we have control of the socket. So we thought maybe we should do this in Erlang. And other people at Ericsson thought that we were mad. But they stopped thinking that nowadays. So let's have a look at the requirements of the TLS protocol. So to be able to communicate, we need to agree on the algorithms. So we need some protocol messages to try and do this. And yeah, Erlang was designed so that it should be easy to send and receive messages. And also, while agreeing and calculating shared secrets that we can use for the payload encryption. So we need to keep track of state information and perform state transitions. It's a generic FSM. And, you know, Erlang was designed so that it should be easy to implement generic FSMs. And also, we have this thing called certificates. It's like a passport, you could say, to do the authenticity part. And they're specified by ASN.NET. So we need to be able to handle ASN.NET specifications. And you know, like Ericsson is a telephone company, and lots of telecom protocols are defined with ASN.NET. So that's a good fit too. The main kind of use of TLS is HTTPS. And there's lots of other protocols that use TLS too. But if you want to keep your users happy and your website's working, you need to have a lot of concurrent connections. And building telephone switches, you also need to have a lot of concurrent connections because you have lots of telephone calls going on. And they're concurrent, and there are many, because there's many people in the world. So, and of course, being secure, you need to be fault tolerant. And in the telecom world, we have a special saying for that. It's 9 nines. It means you can have virtually no downtime to your system. So, up until now, this is a really good fit for Erlang. There's one more requirement, though, on TLS, and it's performing public key and cryptographic operations. And this is a kind of number crunching thing, and this is not a good fit for Erlang. So we should use the right tool, and we still use OpenSSL cryptolib to do all the cryptographic operations. And this is not something that you should reinvent. There's lots of timing issues and pitfalls. So we use well-tested cryptolib for this. And before I go on to talk about the trade-offs, I would like to show you this picture. And it shows you what we gained in scalability by using Erlang to implement the TLS protocol. So the first in OTP 13, that was the old solution, only using OpenSSL. And you can see it scaled very, very poorly. And this is a benchmark run several years ago on an old machine, so please pay more attention to the trend than to the actual numbers. OTP 14, it's the first version where we used the Erlang implementation, and it was just the make it work version. We didn't do any efforts to make it scale or fast. We just wanted to make it work. And then we removed a few bottlenecks, and you can see it scales really well now. And we actually didn't do a lot of optimization efforts of the handshake, so there's still potential to be even better. But let's get into the security versus interoperability trade-offs. So in 2010, we had this choice. Should we follow the spec and check the block cipher padding, or should we interop with Google? So, at the time, there was no known problem with not checking the block cipher padding. Actually, in SSL 3.0, it wasn't even part of the spec. And not interoperating with Google, that is not really great for business. So we didn't follow the spec. We took out the check to interop with Google. And ironically enough, in 2014, the Poodle attack was discovered by Google. And this is an attack that uses this block cipher padding and to manipulate padding and to observe the errors. And finally, they were able to decrypt messages. And this actually rendered the SSL 3.0 protocol obsolete. So it's not recommended at all to use anymore. And of course, TLS 1.0 without the padding check is also vulnerable to this attack. So what happened is Google fixed their servers, and we put back our check. So the next trade-off, you need to understand a little about certificate chains. So a certificate chain is a chain of trust. And you have the root certificate, that is a self-signed certificate. And this certificate you need to own or know on forehand to be able to verify the chain. So you cannot just send it, you have to have it in your certificate store. And then we can have one or more intermediate certificates. And finally, we have the end entity certificate. That's the certificate of the client or the server. And the certificates, they point to each other by their issuer name. And there's a problem also because certificates are identified by the issuer name and the serial number. But the serial number is often not part of the pointer to the issuer in the certificate. And this complicates stuff. And when you're verifying the validity, you do a lot of checks for each certificate in the chain, and you check that, okay, I trust this root certificate. So, no, sorry. So there's different types of chains. So according to the TLS 1.2 specification, we have the first chain. And you have to send the whole chain except for the root certificate. As the root certificate you should own anyway, so you don't have to send it. You can send it, but you don't have to. And also there's this whole standard that specifies the certificates, and it says that it's okay to say that I trust intermediate certificate 1. And if I say that, you will do the chain validation and pretend that intermediate certificate 1 is the root certificate. But you still have to send all of the certificates. That's what the spec says. But as it's complicating building the chains, some software would build them incorrectly, and they would leave it up to the user kind of to configure it correctly, which is not a great thing. So configuration errors led to that some TLS implementations started to accept other types of chains, like this incomplete chain. So here, this is not according to the spec, but many times it would be possible for the server or the client to build the complete chain because they might have the intermediate certificates in their certificate store. So if I get an incomplete chain and I can build a complete chain, I could make this a valid request. And also, even worse, I think, is the unordered chain, because it says the chain should come sorted on the wire, but it doesn't always. So then you, of course, you could try to resort it and see if it works. And a lot of pressure was on us to implement the handling of incomplete chains and unordered chains. But it was breaking the spec, and we were kind of okay. Last time we broke the spec, that wasn't really good. So we were reluctant. But then TLS 1.3 standard came, and they actually standardized that you should do this. So OTP 21 will now do this. And of course, there's a performance penalty doing this. So we implemented it so that the clients and servers, that do the correct thing, they won't get the penalty. The penalty will be on the ones that sends unordered and incomplete change. I'm not going to go into all these attacks in detail, but I want to mention them because they're valid trade-offs. There's something called the Beast attack. It affects SSL 3.0, TLS 1.0, and it takes advantage of certain data being predictable. And it's part of the specification, so we can't do anything about it. So the only way to avoid it is to use TLS 1.2. Then there's the crime attack, and this is an attack on compression. So if you can get a man in the middle and inject things, and you can observe that the message size, because if you inject something correct, the message size will be smaller. But if you inject something incorrect, the message size will be larger. So you can perform attacks on compression and guess HTTP cookies, for instance. So actually, for us, this wasn't much of a problem because we hadn't implemented compression yet. So we could strike it out of our to-do list. But you should be aware that you get vulnerable to this attack even if you use HTTP compression. So compression that is not part of the TLS protocol, but it's run on top of the TLS protocol. So HTTP compression is a security risk. And also there's something called renegotiation in TLS. So you can renegotiate secret parameters. And this is a flaw in the spec too, because they forgot to tie this renegotiation to the session. So then you make room for man-in-the-middle attacks. So they had to do a whole RFC of how to fix this. And here's also an interesting trade-off, because even though the OpenSSL implementation actually came out with their patch like a few weeks before we did, Erlang servers were secure before many OpenSSL servers were, because it's much easier to just load a BEAM file to fix your security problem than to maybe change your operating system to get a new OpenSSL. So if you have a TLS setup with an RSA certificate, and you use an algorithm called the RSA key exchange, you will not get forward security, because even if your key is secure right now, they could save the communication of what you're sending, and later, if your key is broken, they will be able to decrypt. And this is not something that you want. So this kind of makes RSA key exchange not usable. So there are other key exchanges with elliptic curve, Diffie-Hellman or Diffie-Hellman, and you can still have RSA keys. So there's nothing wrong with the RSA keys. And already back in 1998, a guy called Bischenbacher, I think that was correct, I don't know. Well, anyway, he had an attack on the padding used. This is another padding, but it's a weak padding. So the RSA key exchange is broken for another reason than the forward security. So RSA key exchange is broken. But actually, TLS 1.2 still uses this padding. It does have a software prevention, yeah, but it hasn't changed the padding. It was like only now that in 2018 that the TLS 1.3 standard actually obsoletes this padding that was broken 20 years ago. You know, sometimes progress is too slow. Actually, if you have RSA key exchange ciphers enabled on your server, they can be lost in the list of ciphers to use. But if you have them enabled, they can break your RSA key of your certificate. And this is not good. And this is actually the only vulnerability issue written on our Erlang implementation. Because you know the software prevention I was talking about? Well, it turned out we have forgot to put that in. So it was a logical error on our part. But we were not alone to be affected. Many big companies were affected. Cisco, IBM, Symantec, big languages like Java and Haskell were affected too. And actually we did 3 patches that we released like in the same time, making the window when you could be vulnerable as small as possible, so that because once we announced the patch, we announced the vulnerability. So if we did our best to make you secure. TLS protocol has a version negotiation that is kind of sophisticated, but there are buggy servers around. And, well, browser implementations thought, oh, this buggy server, I want to interoperate. So they did their own trial and error version negotiation, which actually mandated that the protocol had to implement mechanisms to prevent version rollback attacks. So even when the security guys get it all right, someone else can mess it up. Oops, this is... yeah, and what about the Heartbleed? This, I think, is the most serious problem in the history of SSL, TLS. Yeah, and it really leaked everything, you know. Keys, password, users, secure documents. Well, it was a buffer override problem in OpenSSL. And, you know, Erlang doesn't have pointers or explicit memory handling. So we don't get these kind of bugs. Of course, as I said, we're not immune to security issues. We can do logical errors too, like the Bleach Basher, but it keeps us safe from a lot of scary errors. It really does. Oops. We also use the commercial test tool, of course, to try to make certain that our TLS implementation is working well. We disallowed 2 next protocol messages in a row, which is an error, but there's no really known exploit of this, not at the time anyway. We did a few more graceful close downs. We gave another error message for TLS record version numbers, so this should be a message authentication error if it's incorrect. And we removed some algorithms from default values. But we didn't really find any serious problems. Making the right choices when it comes to interoperability versus security is hard. And starting of OTP 21, we want to make these interoperability issues a conscious choice of our user. So that's why we removed a lot of default values. And actually, one of the most common error reports on OTP 21 turned out to be interoperability issues with servers that want to use RSA key exchanges algorithms. And also, I'd like to say a few words about what is new and hot in OTP, our TLS implementation, OTP 22. So we have a TLS 1.3 experimental server that is runnable. And also one of my colleagues, Peter Dimitrov, has put a pull request if you want to try out the runnable client. So it's there on GitHub. And we also did some debug logging in the higher throughput optimizations, as you might remember Kenneth mentioning. So let's talk about distribution throughput. We have done some benchmarking, and we took OTP 21.2 because there were some performance issues in OTP 21.0, but the SSL application is from 21.0 because we wanted to have the version of SSL where we had done no optimizations. So most of the optimizations we did will benefit even ordinary TLS connections, but some of them are specific to the distribution. And we did this because, you know, cloud is still a buzzword, and that means our customers want to run Erlang distribution over TLS. So the biggest issue is with small packets, which actually is very common when you run Erlang distribution. So that you can see that small packages the throughput has gone up quite a lot. And actually most optimizations are present in OTP 21. And we did things like we use active N internally instead of active ones. We have tightened loops. We made the outer state record a lot smaller. And we handle binaries in a different way. And also for the TLS distribution, we try to collect as much data as possible before sending it. So if you're really interested, the code is open source. Why I keep doing this? Okay, we also added a debugging level, or a debugging level for logger. So you can actually get the whole TLS handshake on Erlang term format, and it's really nice. And we also added the debugging level of what goes out on the wire. And it's maybe not as user-friendly, but it's comparable to OpenSSL logging, and that can be pretty useful. So please try out OTP 22. And remember, don't linger too long in the past, because many security problems comes from you're not upgrading your systems so that you're vulnerable to things that was found and fixed a long time ago.
In Erlang, you call, of course, your C code for your cryptography. So if you want to sign a message or you make a new key or whatever, you do that in C. That's all very trusted, and you have some NIF, you do the whole thing. Now, if you look at security protocols, then in the C side, they often do something with your secret key, and then they zero out the memory. And in particular, if you're on a cloud server, it might make sense to zero out that as quick as possible, so that no one can use a core dump or whatever to look into your memory. In Erlang, if you send the secret key your C code, the C code then zeroes out that part of it. But of course, it's still in the Erlang world as a secret key. So if you would get a core dump, it would still be there. So it would be extremely useful if you could tag certain data in Erlang as being never ever look at this. And of course we have that because we have this process sensitive flag set to true. But not really on the level that you want to when you send it to your NIF process. It may still be visible in the Erlang VM, but not on the C side. So is there any thought that you have had to kind of look into that and protect keys in Erlang in a better way?
Well, that's something that we, of course, can think of in the future, but I have one solution for you, and that is that we support OpenSSL engines. So you can have your special engine, like that puts your secret key on a little special hardware card, and nobody can access it, and you can access it, and you can use it through Erlang.
But that would not work if I run my web server in the cloud.
I'm not sure how they're thinking about that, because actually this was motivated by people saying that's how we have to do it in the cloud, because in the cloud you can't trust anyone, because you're on a computer together with maybe your worst competitor. But you will, of course, get a higher latency if you're going to talk to some hardware that's somewhere else. But if you want to be secure, fine.
Yeah, in Firefox, at least in nightly builds, you can run it with some environment variable set, and then it will dump all the keys for SSL connections into a special file. Yeah, that's really good for debugging. If you have something on the other end, you want to debug it. Then you can feed the traffic and these keys into Wireshark and see in plain text what's going on. Is it possible to get something similar in Erlang?
Well, we have some exportable, so you can get keying information, because there are other protocols actually that, like, they set up a DTLS connection, and then they export out the secrets, and they use it for some kind of different protocol that has nothing to do with DTLS. So there are such functions, and the reason is security by obscurity doesn't work. So if you have access to the Erlang node, you will have access to the keys.
Yeah, I mean, is there any easy way? Like, of course, I can dig into the code and get access to those keys.
We have SSL connection information, and it can export such information in the same way as OpenSSL would.
Okay, thank you.
How do you handle binaries?
Well, I recommend you to talk to my colleague Raimo. That was the one who implemented this part. Talk to him after.
Is there any plan for Erlang OTP team, or maybe it would be a law for Erlang Ecosystem Foundation to have some sort of CSIRT team? I mean, the Computer Security Incident Response team for such kind of emergency, if it's sort of emergency like Heartbleed or Poodle happens.
Yeah. Well, there's this security group in the Erlang Foundation. I'm not sure yet actually how it will work, but we will participate. But I suppose it's up to the OTP team to fix security bugs if they happen, and we try to fix them as quick as possible. And normally when we get bug reports, we fix them in a day or two.
So if you suspect that there is a security issue, you should not report them in the ordinary issue tracking system. You should report them this way, and we handle them with high priority and contact other security organizations and so on. And if it should be reported as a general vulnerability, which you usually maybe don't do until you have a fix for it. Normally you report the problem together with a fix, if you can. If you can solve it in a few days or so.
Are we okay to say, okay, build Erlang with the FIPS flag on, and then securing your distribution links with TLS? Or is there more that we should be doing?
Well, I think there is something more you need to do. But we interop with all OpenSSL versions. So if you build it FIPS, but I think you have to do something in runtime.
Okay, another hand for Ingela, guys.